The focus of this lesson is just to kind of declare what the second derivative can tell us. You know, from our main function, we can find the x-intercepts and the y-intercepts. And then when we start taking the derivative and analyzing the derivative, we can find the potential points, the critical points, where the graph will go from increasing to decreasing and decreasing to increasing, so like maxes and mins. And then from the second derivative, what we're finding out is we can tell points of inflection. And points of inflections tell us when the graph is shifting from concave up, which is like a bowl, to concave down, which would be an upside bowl. Okay? And so obviously if the first derivative is positive, that means we have a bowl that's shaped up, and if the second derivative is negative, we have a bowl shaped down. So second derivative up and second derivative down, positive and negative. Okay? And when the first derivative, when we set that one equal to 0, we find our critical points. So in the second derivative, if we set that equal to 0, we have these potential points of inflection where we're going to switch concavity. The second derivative test basically just tells us that if the first derivative equals 0, which means that my graph has gone horizontal, I'm looking at either a max or a min. If my second derivative is less than 0, then I'm concave down, and obviously I have to have a max at that exact same point. So at x equals c, or x equals 1, for example. So if the first derivative is 0, telling me I have a potential max or min, specifically if my second derivative is negative, then I have a max. And the opposite of that, if my first derivative equals 0, so I'm finding a potential max or min, if my second derivative is positive, then I've got to be faced up. And then third point is if they're both equal to 0, then we can't really tell too much without really just graphing the function as is. So some steps on how to graph a function are listed right here. First of all, we're going to look at the domain, check to see is your function, does it have any radicals in it? So we have to worry about that. Are there any variables in the denominator? So that's one other thing we've got to look for. If your main function is a trigonometric function, then for graphs like secant, we can't do anything with pi over 2s, multiples of pi over 2. If you're looking at cosecant, we can't do multiples of pi and 0. Okay? We want to find the next, both the first derivative and second derivatives. From the first derivative, we're going to set it equal to 0, find the potential critical points, and then determine our intervals of increasing and decreasing. From our second derivative, we're going to set it equal to 0, find our potential points of inflection, and then determine our concavity from the second derivative. Okay, and last but not least, we're going to look for obviously asymptotes, and that's really going to check off more with the domain part to see if there's anything in our domain that's undefined. That's will be our asymptotes, and then find other key points like our intercepts. And again, the intercepts come from just our main function as is. Okay, so let's go to example 1. For part A in example 1, and then also for part B, which we'll do here in a second, we want to identify the inflection points, the local maxes, mins, and the intervals of concavity. So it looks like we need to focus on finding the first and second derivatives. Okay, they've given us a temporary graph that we can kind of look at, but we're going to obviously get more of the actual exact numbers where everything changes by using the derivatives. Okay, well this first main function, if I took the derivative as is, it looks like I would have to use the product rule because I've got a variable here and a variable in there and they're multiplied together. So we could do that, that'd be fine. Or what we can do is just clean up the function first of all. We can write it as y is equal to 9/14. Let's see, x to the 1/3 and x squared combined together will be 7/3. And then minus 9/2 x to the 1/3. Okay, so just a little easier function to take the derivative of if you want to kind of look at it like that. So y prime, by the time I bring down 7/3, the 7 and the 14 are going to reduce, the 3 and the 9 are going to reduce, so that'll give me 3/2 x to the 4/3 minus, and if I bring this one down, we'll get 3/2 x to the negative 2/3. Okay, and for the second derivative, again bringing down the 4/3 and reducing there, we'll get 2x to the 1/3, and it's negative out front, but when I bring down that negative exponent, it will become positive x to the negative 5/3. Okay, so there's our first derivative, our second derivative, plus our main function. And from there, let's set each of these equal to 0. So when y prime equals to 0, we're going to get 0 equal to 3/2 x to the 4/3 minus 3/2 x to the negative 2/3. So kind of cleaning this up a little bit, we'll get 3/2 x to the negative 2/3 is equal to x to the 4/3. Sorry, got the 2/3 part, or the 3/2 part. So 3/2 x to the 4/3. Okay, obviously the 3/2 are going to reduce off of each side, and I'm left with x to the negative 2/3 is equal to x to the 4/3. Okay, right away, right there, for potential critical points, I'll list these over here. For potential critical points, I know x equals 0 is 1. Because 0 to any power is going to equal 0 to any power. So there's a potential one right there. But to see if there's any more, let's get rid of these fractional exponents. If we cube both sides, what that's going to do is, 4/3 times 3 is just 4. Negative 2/3 times 3 is just negative 2. So we have x to the negative 2 is equal to x to the 4th. Okay, so right there, now, just like what I did with x equals 0, is I know that 0 to any power is going to equal to 0 to any power. But specifically for these squares in the fourths, I know that x equals 1 is also 1. Because 1 to the negative 2 is 1, and 1 to the 4th is also 1. And similarly, we can also consider x equals negative 1 part of the group, because negative 1 to the 4th power is positive 1. And that right there is just saying 1 over x squared. So if I plug in negative 1 right there, you're obviously getting 1 as well. So there are our critical points, x equals 0, 1, and negative 1. Okay, now before we go ahead and do the whole local maxes and mins and testing for that, let me go and take the second derivative. Let's set that equal to 0, and then solve for the points of inflection on that one. Okay, so when we do the second derivative equal to 0, it's saying 0 is equal to 2x to the 1/3 plus x to the negative 5/3. Okay, or we can say 2x to the 1/3 is equal to a negative x to the negative 5/3. And let's go ahead and cube both sides, so that way we can get rid of some of those fractional exponents. So we'll get 8x is equal to, when I cube a negative, it still stays negative, and this will be x to the negative 5. Now with this, it's a little more easier, I guess, to even point it out. The only thing that x can be on both sides to really set it equal to each other would be 0. And as you can even look at on our graph that we give an example that only here at x equals 0 am I changing my concavity. But the reason why is because they're both odd powers, but because one has an 8 in front of it, the other side has a negative 1 in front of it, that's even alternating the dimensions of everything. So as far as our points of inflection, I'll put P of I for points of inflection. It's only going to be at x equals 0. Okay, so from there, let's get our sign charts, and for both of them, a sign chart for the first derivative and a sign chart for the second derivative. And with each of those charts, or the number lines if you want to consider it, what we're going to do is put on for the first derivative, we're going to put on our critical points. And then for our second derivative, we're going to put on our potential points of inflection. So here will be the first derivative. I guess I'll call it y prime. And then on there, we're going to put negative 1, 0, and 1. And we're going to test for pluses and minuses. And then for our second derivative 1, we're only going to put on 0. And we're going to again test for positives and negatives in that one. So for the first derivative, remember I'm going to be plugging into the first derivative equation. And if you guys want to just pause the video for a second and plug in some values of your own, like we could test negative 2, looks like maybe a negative 1/2, a positive 1/2, and a positive 2. And then for the second derivative, let's just test negative 1 and positive 1. So why don't y'all do that? I'll do it myself, and let's come back and see if we get the same values. Okay, so I went ahead and did my sign charts, remembering that for when I'm testing for intervals of increasing and decreasing, I'm plugging my potential values into the first derivative. And when I'm testing for concavity, then what I'm doing is I'm plugging my potential values, like negative 1 and 1, into my second derivative. Okay? And just kind of analyzing the graph too, it looks like it's reiterating exactly what I found. everything up to -1, my graph is increasing. So it looks like right about there I actually have my -1. So my graph is increasing up to -1. And then between -1 and +1, even past 0, my graph is going down and going down. So obviously right about there is when I'm going to get +1. And then after +1, because my first derivative is telling me it's positive, that says my graph is increasing. Okay? And then what my second derivative test is telling me is that everything left of 0, I should have a bowl shaped down, which is exactly what happens. And that everything to the right of 0, I should have a bowl shaped up, which is exactly what's happening. Okay, so then to answer the questions, I have a local max at x equals, looks like -1, and I have a local min at x equals +1. And then from my second derivative test, I am, what it tells me that my graph is concave down from -infinity to 0, and then I'm concave up from 0 to infinity, and then obviously my points of inflection are at x equals 0. My critical points are 0, 1, and -1. Obviously at x equals 0 I didn't really get a max or a min, but it definitely was a critical point. I had a potential value there for a max or a min. Okay, so let's go on to the next example.